Hello, everyone. Today we're returning for our second semester. It's a pleasure to have all of you back here at the Brazilian Singularity Theory webinar. This semester, our webinar is being organized by the Singularity Theory groups from USP São Carlos, Universidade Federal de Sergipe, Universidade Federal da Bahia, Universidade Federal de Uberlândia, Unilab, and Universidade Federal de São Carlos. This last one represented by our new member in the organizing committee, Hellen Santana, who is also the speaker today. And I also would like to use this opportunity to ask you something. So please feel free to send us speaker recommendations. You can do this by mail, sending an email to brsintheorywebinar at gmail.com. And now it's my pleasure to introduce today's speaker, Hellen Santana from Universidade Federal de São Carlos, who's going to talk about Chern obstruction of collection of one differential form and applications. Thank you very much, Hellen, not only for accepting our invitation to this talk, but also to be part of our organizing committee. Thank you very much. Can start now.
Thank you, Igor. Hi, everyone. Bom dia, bonjour, buenos dias. It's a very big pleasure for me to be here contributing in the webinar, Brazilian webinar in Singularity Theory. Actually, this webinar reminds me of the seminars we had in ICMC here in São Carlos. And it was a great pleasure for me in 2017 to somehow organize these seminars, and now to see it's to me similar. It's a similar project, right? But now it's kind of better because we have the opportunity to have a lot of institutions, people from a lot of places in Brazil, and also to be able to have people from around the world to participate in this webinar. So it's very nice to be a speaker, but also to be again organizing this seminar. So it's very nice. Thank you very much for the invitation. Thank you everyone for coming. It's a great pleasure to have you here, some friends and advisors and people who I admire. So thank you very much. So maybe you already saw me. Some of you already saw me talking about these topics I'm saying today. But still, I think it's a good opportunity to discuss some definitions on important invariants that we have in singularity theory. So this is what I'm going to do. I'm defining a lot of things, and then I'm going to end this lecture with some results that I got together with some collaborators on this matter. All right. So. Well, this was my introduction. So let me just skip to the description of the setting. So we are considering reduced complex analytic germ of dimension Gx. So like the zeros of a finite number of holomorphic functions. And we give to this set, to this germ, to this space, we give a witness stratification, all right? So we do have some regularity in this strata. So what we have here is a decomposition for who don't work on this subject. What we have here is a decomposition on smooth subvarieties of X, and there exists some regularity condition between this strata. This is what is happening, and we always can give such a stratification for this space. All right. We are also assuming that one of those strata is the zero set, right? And also the VQ, the last one of them, the bigger one, is the regular part, all the set of regular points of the variety X. All right. So something that we can use to study the singularities of a complex analytic space is the local ILO obstruction. And I'm taking the time to see the definition and then to understand how this invariant is defined, all right? So what we have is the following. Our variety X over here, a better thing would be to construct the diagram, but we are doing this we are going to understand this diagram with it already constructed, right? So we have our complex analytic space X in an ambient space U in Cn. And then we consider the Cartesian product of U to the Grassmannian of D planes in Cn. And between these two spaces, we have a restriction, the projection in the first inter, right? And the ambient space, this element is the ambient space of a space called the Nash modification. Well, in the Nash modification, we would have the following. So I do not write this, but I'm going at least to explain it. So this is the Nash blow up for who use this language, but the thing what we have is the following. We always have pairs. In one entry, we put a point, and the other we are going to put a linear space. If the point you took in the first entry is regular, the linear space you take is the tangent space of the regular part, the regular part of the variety at that point. If it is singular, we consider a sequence of points and converging to that point which is singular, a sequence of regular points. This sequence of regular points, at each one of them, we can compute a tangent space, right, to the regular part. And then we have the sequence of points produces a sequence of tangent spaces. And this sequence of tangent spaces converges to some element in this Grassmannian manifold. So what we have is the point, which might be singular, and in the second entry, we put the limit of sequence of tangent spaces we had in this construction. All right, if you have any doubts, you can ask me, and maybe I can write it, but this is what is happening, right? So what we have here is the closure of the Gauss map. Who knows this language is the closure of the Gauss map, right? So this is the Nash modification, all right? So over this Cartesian product, we take an expansion of the tautological bundle, and we can restrict this bundle to the Nash modification. And this restriction is also a bundle over this space X tilde, our Nash modification or Nash blow-up, right? So this is the diagram that we are going to use to construct three invariants. The local obstruction that I was telling you that is used to study the singularity of a space. The Euler obstruction of a function, which is used to study the behavior of a singularity of a function with isolated singularity defined on X, defined on this space, and also the Chern obstruction. The Chern obstruction is a more delicate, even more delicate, in my opinion, invariant, but still, this is the diagram that's going to base the construction of these three invariants. All right? Okay. So to construct the local obstruction, what we do is the following. We start with a differential form, omega, giving like this. So this z bar square, this z bar over here is giving like this. So n is the dimension of our ambient space, all right? So this is the one differential form we started with. And then using this projection, we can take the pullback of omega through this phi. Okay, I don't know, this element, all right, this function, this projection. And then we can restrict this pullback to the Nash modification. And then we obtain one differential form, one form over the Nash modification. And then we can choose a small epsilon over when we look at the omega tilde over this a small sphere with this epsilon, a sphere with radius epsilon, a small epsilon that we took. Okay, I'm a bit nervous, but all right. So we take this is a small epsilon over which we have omega being non-zero of a small sphere with that radius. All right. And then this omega could be seen as a section of the dual Nash bundle. I do not know if I told you, but the restriction that we took from the tautological bundle to the Nash modification is still a bundle that I told you, but also is called the Nash bundle because it's the bundle over the Nash modification. All right, so this omega tilde can be seen as a section of the dual Nash bundle, of a section of this bundle over here. And then we take this small epsilon and a sphere over which we have omega tilde being non-zero over that sphere. And then obstruction theory would say, would measure if it is possible or not to extend omega tilde from this small sphere into the ball. All right. So what we are doing here is like this procedure that I'm telling you, we are doing this in the right dimension. And that means that we can make these extensions for a lot of dimensions, in a lot of dimensions. And there is some of these dimensions, which is like 2D, because D is the dimension of our variety. So in the dimension 2D, there is some information about the difficulty to make this extension. This is what is happening. So we are working in the right dimension to collect some information, right? So the obstruction theory would say that to make this extension from the small sphere into the ball, into this sphere, for the interior of the sphere, this is a cochain, which is actually a cocycle. That means that we have an element in this cohomological group. What we're doing is to extend our omega tilde from the sphere. Over here, I'm using the inverse made of a map because of the following. Between the Nash modification and X, we do have a certain map, and we actually have our sphere over here in this level. You can see, right, the small hand that there is here, the cursor, right?
Yes, we can.
Yeah, okay. So here we have our sphere, and we are looking at inverse image of this map which exists between these two varieties, right? So this is why there is this, the inverse over here. But we are trying to extend from this sphere into the ball, and what we obtain is a cocycle in this cohomological group, all right? I hope it was followable, and if not, you can ask me, okay? So this element, so this is the cocycle I'm saying, and associated to this cocycle, we have a cycle in the correspondent homological group, all right? And then if we make the evaluation from this cocycle to this cycle, we obtain an integer number. We are working we are working over the integer numbers, the set of integer numbers, and we obtain an integer, which is the local obstruction. All right, so this is the local obstruction of the variety X at the origin. Okay, so this procedure is possible. It was a remarkable work of Macpherson when he proved the existence of Chern classes for singular varieties, and he made all this construction using one differential forms, right? And it works for a variety with singularities, right? It works for a singular variety. I want to also mention the work of Marie-Hélène Schwartz and Professor Jean-Paul Brasselet, who make this equivalent construction, independent equivalent construction using vector fields, right? So this is also possible to be done using vector fields. All right, so this is the local obstruction. And since the local obstruction is a very powerful tool, I mean, it is obviously, it's not easy to construct. There's a lot of deep topological, in my point of view, things to understand. So it is not easy to compute this number. So due its power, many authors gave alternative ways to compute the local obstruction. And here, I think I'm in a safe place to say that here, when I used to present my project during my PhD, at this point, I would say that it was an easier way to compute. And then, making lectures, we learn a lot. And then I understand that it's not easier at all, because we should use here, I'm going to explain this formula, but here we have a genetic linear form. And it is not always easy to find such a genetic linear form. So it's not actually an easier way. It is an alternative way, and it's not as difficult, might be not as difficult as the doing by definition, which is usual in math, right? But the thing is that we should have for X, for the variety X, Whitney stratification. So this VI over here are Whitney strata. And the local obstruction is computed as this summatory. So here we have the Euler characteristic of the inverse image of a small value, delta, by a linear form, by a genetic linear form. VR are the Whitney strata in a small sphere BX. Right? So this Euler characteristic is multiplied by the local obstruction at a point of the strata of the Whitney strata. And this is possible because it is proved that the local obstruction is constant on a strata of a Whitney stratification. So this is why it is written like this. All right. So this is what Bracellele and Sade proved using this genetic linear form. All right. Okay. All right. So the thing is that my interest, and that I should mention in the introduction, but I'm saying now, is that my interest is to study singularity, the topology of a function with non-isolated singularity. And that means that we have a function f defined on our compact analytic space, and there f has singularities both coming from the singularities of x, the singularity of the variety is a singularity of f, and also the singularities of f itself, which is of intrinsic to f, right? So there's these two types of singularities, the singularities coming from the space and the singularities intrinsic of the function f. So it is important in this point of view to have a tool that would describe the singularities of x, the space, the domain, and the singularities of f. This is what is happening. The tool choosing by the works I follow, and I'm saying this works in the sequence. But the tool they chose was the local obstruction, and there is another invariant associated to the function f that has a similar construction to the local obstruction. And this invariant is the Euler obstruction, not local, the Euler obstruction of the function f. Let me just use this slide over here, is because what we have now is a function f defined on x and isolated singularity at the origin. This is what is happening. And in the setting, using such function, Bracellele, Massa, Parmesani, and Seade made the following construction. They kept this diagram, and the thing is that instead of using that one differential form that I told you, using like the square of distance, roughly speaking, the square of distance in Cn, they used a one differential form. Actually, they made the construction using vector fields, but just to follow the setting I started with, I'm keeping the differential form language, all right? So they use a differential form, they construct this differential form using the function f. They use actually it's a differential form close to the gradient. You know, the partial derivatives of f, and so on. But I'm not writing it over here. Is not the purpose of the lecture. It's just to show you how close these three constructions are. All right. So they construct a one differential form using f, the function f, and they make the same procedure. I'm not saying that it's easy. It's a very hard, very deep topology things being made in that paper. I'm just saying that the things are close. To construct the right differential form is not easy. They made this such a construction, all right? But to see the definition is quite similar to the local obstruction. So let's go. They have this one differential form associated to the function f, and then they make the pullback over this projection, restricting to the Nash modification, and then it can be seen also as a section of the dual Nash bundle, and then take this small epsilon over the, so this omega tilde, the omega tilde they constructed, right? So this one differential form would be a non-zero section over a small sphere, and then again we can apply obstruction theory to produce a cycle, which is the obstruction cycle, to extend omega tilde from the sphere into the ball again. All right. So the change was which one differential form is good to give the information we need. So this is the difficult part, right? So when we do that, we also have this cocycle obstruction that can be evaluated to a cycle in the correspondent homological group. And then making this evaluation, we have also an integer number. And this integer number they call the Euler obstruction of a function. And I think they were, the name is quite inspired by the closed construction, right? And is related, and since they used the one differential form that came from the function, so it's natural. The name is quite natural, right? So the Euler obstruction of a function is this integer number that appears in that construction. I hope you can follow the idea. If not, you can tell me, all right? Okay. So not only they made this difficult construction, in my opinion, they also relate the Euler obstruction of a function with the local Euler obstruction. And then they prove this formula. So the Euler obstruction of a function is the local Euler obstruction of the space X minus this summatory. And I told you that my interest was to study the singularities of a function f. The best case would be in the non-isolated singularity case, but let's understand what happened in the isolated singularity case. So this is what I am interested in. So it's an invariant associated to the singularities of f, related to an invariant associated to the singularities of the space X. All right, and they prove that this is the difference, the defect, and this word will appear after the defect comparing these two numbers. All right, let me see the time. Okay. And if you see here, what we have is the summatory of Euler characteristic multiplied by the local Euler obstruction. And the difference between this summatory and this one is that instead of a genetic linear form as we had here, we have the function f itself, right? Vi still are our written stratum, and this is quite interesting, right? The thing is that if we compute the Euler obstruction of a genetic linear form, then if we do that, we obtain 0, right? Because the local Euler obstruction is given by this formula over here, and this would be 0. I should have write it, but you would be 0, right? Okay. All right. So not only we have this very interesting formula, we also have a geometric interpretation for the Euler obstruction of a function. This was made by Seady, Tibard, and Verzobsky. This is a very nice paper, and the thing is that they prove that the Euler obstruction of a function is a number of Morse points, the number of Morse points in the regular part of X, sorry. Didn't put it here. But the thing is that when you have a singularity, at the origin, this is the case, right? When you have a singularity at the origin, this singularity might be degenerated. And this degenerated, it would be related to the Hessian matrix, the matrix of second derivatives. So if that matrix is singular, if it does not have maximal rank, then we have a degenerated singularity. And this degenerated singularity, if you perturb, this is not easy also. I'm just telling the story already concluded, right? I mean, it's difficult work, but once you deform the function f, you can explode this singularity at the origin into finitely many singular points, right? So you produce a certain number of singular points. These singularities might be in a lot of these singularities might be in different dimensions, in different strata. Let's say like this, all right? Remember, we have that Whitney stratification. So we have the zero strata, and we can go up through dimension until the bigger strata, which is the regular part of the space X. So the singularities might be in different dimensions. And what they proved is that the Euler obstruction of a function compute the points that appear in the bigger strata, so in the regular part of X, right? Okay, if you have any doubts, you can please feel free to interrupt me, right? And okay, so and then they proved this. This is quite interest also looking historically, because the Euler obstruction of a function has this formula. Over here we have a fiber, and if we go to the smooth case, if we go to the smooth case, the case where X is smooth, what it would appear if F has an isolated singularity is what we have if we compute this Euler characteristic is to have the Milnor number, right? And the Milnor number also is related to a number of Morse critical points. All right, so this is quite interesting because we can see this work also through this point of view as a generalization of the Milnor case. All right. Okay, good. Okay. Another interesting thing here is the following. These Morse points that I mentioned here are the non-degenerated critical points that are produced once you deform the function f. This deformation has a face. You know, there is a type of deformation that you can make to the function f that are Morsifications, and then that would produce these non-degenerated critical numbers, these Morse points, sorry. I'm showing this face of this Morsification later, all right? That appears in the following of the lecture. In the same paper, look at this formula. In this paper, they also consider the case of non-isolated singularities. This formula is computed for isolated singularities. But this difference, sorry, let me see. Yes, this difference over here can be also computed for functions with non-isolated singularities. It is not easy to compute, but it is possible, all right? So this left side is not true because for non-isolated singularities, because this is defined only for functions with isolated singularities, right? But this can be done to non-isolated singularities. So in that same paper, Brasileiro Massa e Parmesan and Seadi defined this difference to be the Milnor defect. So the Milnor defect of a function now with non-isolated singularities. All right, so in the case where we have isolated singularities, the function with isolated singularity at the origin would coincide with the Euler obstruction of a function. This was in 2004. Later on, in 2014, and now you see why I panicked. No, I'm just kidding. When I saw Nicola Duterte in the audience, I'm just kidding. And Nicole, I'm very happy you're here. The thing is that Duterte and Grulha, they defined that different, only this summatory. They focus only in this summatory, and they call the summatory the Brazilian number. All right. So they focus on study the topology, this invariant associated to a function with non-isolated singularities defined on a complex analytic space. The only difference, it is not quite a difference, but the only difference between this setting of Duterte and Grulha and this one of Brasile-Massa and Parmesan-Enseadi is that over here, VI are strata of a Whitney stratification. And here we have a good stratification. Since all these things are not light to digest, I will not give the definition of the good stratification, but it is also a decomposition of our variety X. And we have some technicalities between the variety X and the function f. So we would see which, like, we would divide all this collection of subvarieties V1, VQ. This not only the V1, VQ, here the V1, VQ. Anyway, we would divide the varieties of the stratification into those who are in the zeros of f, that has some intersection of the zeros of f, and others who has non-intersection with the zeros of f. This is what we do. And looking at these two worlds of strata, we would require a certain regularity condition. All right, the AF-Tom condition for who knows this language. But the thing is, for you that do not know yet this language, the thing is that we have this regularity, all right, between these two worlds of strata. And also, and this is why I said that here we had not such a difference between not such difference with the other case, the other setting, is because out of the zeros of f, not only here, but in the world of strata out of the zeros of f, we do have Whitney stratification. So look at this intersection. We are out of the zeros of f. So over here, this VI also have the Whitney conditions being valid. So the setting between this world and this one are connected, right? The only thing is that since here we have non-isolated singularity, there is an important condition, a technical but important condition when we talk about the zeros of f. And now actually this is something important, because why we should take into consideration, why should we take care of these things, is because the critical set of f is all contained in the zeros of f, right? So the problem, the difficulty is over here. Not that here is not difficult, but there is a lot of difficulty over here also. So we should have all. It's really okay. Let me breathe. So we should need specific stratification in order to work in this world, all right, in this setting. So this is the Brazilian number. This is a very important number in my life. This was the main subject in my thesis. Duterte and Grulha were my advisors. And then let me just show you the following. The Brazilian number can also be used to compute a number of Morse critical points. All right, so we can also consider, let me just read the statement, and then I will make some comments. So over here, they are computing the Brazilian number of a function f, a function with non-isolated singularities, and also the Brazilian number of the function f in another space. See, here is x, the space we started with, and here we have the space x cut by the zeros of a function g. This function g here is a special function. I'm not going to this. Let me see. No, the thing is that being prepolar, that is here in the hypothesis, is the following. When we restrict g to the strata of the stratification we are using, we only have the zero set. So it had kind of a more powerful isolated singularity condition. This is what it is, right? So if G is prepolar, when we compute this difference over here, we obtain a certain number of Morse critical points. Where they are? Morse critical points of what? So we look at G restricted to the fiber of F. C is the domain of G, the domain we are looking for G, we are restricting G actually, is the fiber of F. Okay, like this. And then we would define this function here, this restriction. We make this deformation, and then this deformation would produce a certain number of Morse critical points, and this is what this difference of Bracelet number is counting. All right. Okay. Now here I'm just let me just say some words more words about this formula. This is where my thesis born actually. So what we did in my thesis, what I did in my thesis was suppose that we do not have this tripolarity condition. Suppose that we do not have this powerful isolated singularity condition over the function g. I only get to the point that g has a critical set of dimension 1. This was my step, but it was a lot of work, even for a function with with a critical set of dimension 1, is a lot of work, a thesis work. So, and there is a formula that we are able to compute this difference of Bracelet number relating to a number of Morse critical points. It is possible, but we should have another more invariants involved, right? This is not what I want to say today, so let me just keep going. This is where I want to say what I meant about the phase of the morsification, the phase of the deformation. And this is what is happening. We look at G plus a complex number multiplied by a genetic linear form. So if we make this type of things, we can, if L is generic enough, we can produce only non-degenerated singularities and make these computations like we are seeing here.
Excuse me, Hellen. Sorry about that. Maybe I missed something. What's the definition of G being prepolar with respect to nu? Say it again, please.
It means that if you look at G restricted to a stratum of this stratification, so we look at G restricted to each stratum, and you take the union, Raimundo. You take the union and then the closure. So this should be only zero, only the zero set.
Oh, I see. The closure of the stratification, the nu is the stratification of X, right? Or what?
Yeah. Yes. This stratification is to X, is of X. Yes.
So when you take the closure and they each will only intersect at the oranges, that's correct?
Yeah.
Oh,
yes.
I see. Okay,
you actually not intersect is the union, right? The union of the critical set of G restricted to the stratum.
The union of the critical set of G. Oh, I see.
Yes.
Oh, okay, much better. Okay, thanks. Thanks for that.
Thank you, Raimundo. Okay. Now we are moving to the work of Ebli and Guzenzade. And I'm not going to, you see, it's kind of scary for me. It's kind of scary the following the slides that are following, but let's just talk about it. Instead of working, let me see. I'm going to take I put it here. Instead of working with one differential form, like we saw in the construction of the local obstruction and the Euler obstruction of a function, Ebli and Guzenzade worked with a collection of one differential forms. So the notation is like this. It's a collection of one differential forms, all right? So for each element in that collection, we can make this procedure, right? Pull back, restriction to the Nash modification, look at the section over a small sphere, and so on and so on. What they did was to look not at each element of the collection, but look at the collection, the whole collection, all right? The level are the same. So we have a collection over here of one differential forms. We take the pullback, we restrict to the Nash modification. Now, instead of having one differential form, we have a finite number of differential forms, right? So instead of having a section of the dual Nash bundle, we have a section of a finitely many copies of the Nash bundle, right? As many bundles, as many elements you have in the collection. And I mean, the thing works. We also obtain, when we can look at a small sphere, see it, the omega, the collection as a non-zero section of this big bundle over here, all right? And then use obstruction theory to obtain a obstruction cocycle to extend this section from the sphere into the ball. It is quite amazing that the thing works, even in this very general case, that this is what Hellen and Universidade proved. But you see, the construction, the diagram you use, the base we use to the construction is quite the same, all right? Okay, so when you look, I'm not going on every detail, but what we do when we make the evaluation of the obstruction cocycle we made, the construct associated to, we make the evaluation of that cocycle at the cycle associated to it, all right? We make that, we obtain an integer number, which is the Chern obstruction, all right? The thing is that this is very nice. It's important to say one thing. Once we change the nature of our elements, we are not saying anymore about critical points. We should define, since we changed the setting, we should also adapt what is singularity for us, actually for Hellen and Universidade. And they define it to be a special point. And I'm saying here, at least roughly, but the thing is that a special point, see, we have a collection of one differential forms, right? If we look at if we restrict each of these elements to a space limit, then we can talk about linear dependency. So a special point would be a point where we have an element associated, a space limit associated to it, all right, a space limit. And when we restrict each element of our collection to that space limit, we have linear dependence. This is what is happening, all right? When I say space limit, I am connecting to the construction we made to the using the Nash transform, right? If you want to know more, I can explain step by step, but let me just keep going because I lose control of the time. But okay. So the thing, what is interesting is that the following. They also this special point. So we adapt to this notion of singularity. So this special point can also be degenerated. Using also looking at, it's quite similar to look at this Hessian matrix, adapted to this setting, but it can be degenerated. And if we deform our collection, we can produce non-degenerated special points. And that is quite amazing for me. Because okay, they would be non-degenerated in the same setting. We look at the Hessian matrix, and that Hessian matrix at that point would be non-singular, would have a maximum rank, all right? And the thing is that the way to deform our collection to produce only non-degenerated spatial points is using a deformation like this. So we take the elements of the collection. Okay, there's a, there we take the element of the collection plus a complex number multiplied by a linear form. If this linear form is generic enough, then we obtain deformation of the collection that would produce only non-degenerated special points. Okay, and this sum over here, this deformation over here, is quite similar to the one we saw in that we saw before, both in the work of Euler obstruction of a function and also of the Brusselin number. All right, I'm going to skip this. I'm going to skip it and just go through the theorem. That is a joint work with Grulha, Professor Nivaldo Grulha, Camila Ruiz from Federal de Berlândia, and myself. That is the following. Since we have, the critical, to produce non-degenerated critical points, we made some deformation, which is of the same type of the deformation Hellen and Universidade did to produce non-degenerated special points. So the question we tried to answer was how to connect the critical points of a function with the special points of a differential form or a collection of differential form. All right. So what we get is that here I didn't say, right? This number of non-degenerated special points, I didn't say, okay, this was the most important thing. These non-degenerated special points that are produced with this deformation is the Chern number. So this is quite similar to the Euler obstruction of a function that we saw there in the work of Seadity, Barton, and Wejovsky, right? So, okay, I forgot that. It's quite a shame, but okay. So the thing is, we could connect the number of critical points with the number of special points in this setting. We take a function f1, tractable at the origin with respect to a good stratification, and the Chern number of this differential form over this intersection is the number of Morse critical points of f1 on this intersection. So this number of Morse critical points is that number of non-degenerated singularities that appear when we make that deformation, that certain type of deformation, some f1 with a complex number multiplied by a generic linear form. And over here we have the Chern number, but the thing is that we connected these two things using the number of special points and the number using the nature of the special points and the nature of the critical points, all right? And using that the deformation to produce both are of the same nature. This is the same type. Being tractable here, it is important, Raimundo would ask. Oh, no, I'm kidding, Raimundo. So everybody should ask. Being tractable over here would be the following. We look at the critical set of f1, f2. f1 and f2 are the function we are using, right? f1, we always, in this setting, we always have two functions. But we should control, f2 is quite wild. It can have has a non-isolated singularity, but we should control the behavior between f1 and f2. And this behavior is controlled using the tractability condition, all right? But this means that we take f1 and f2, and then we restrict to each strata of the stratification. And then we take the critical set, all right? Okay, we make this for all VI. So we take the union, I didn't put it here, sorry, but we take the union over all strata of the stratification. And then we take the closure because we're looking at analytic worlds, all right? So the dimension of this polar variety, you can see that who knows this language would connect with the polar variety. So this is a polar variety. So the dimension of this variety should be at most one. Yes. So the higher dimension is 1. Okay. And also, when you look at f1 restricted to the strata intercepted by the zeros of f2, we should have only the origin. Right? Here we also should do this going through all the strata of the stratification who intercept f2, the zeros of f2, and take the closure. So we look at all the strata, take the union and the closure, because we are in an analytical world. So this would be only the origin, only 0. This is being tractable, right? After with
excuse me, Hellen. Tractable means these two conditions should work together.
Yes,
okay.
Together. I didn't say it. Thank you, Raimundo. The both conditions together. Yes.
Oh, okay, thank you.
And after with Bárbara Lima Pereira and Professor Maria Ruas, when I'm not with you in the audience, Professor Ruas and Bárbara, I always say that was very good luck for me. So now that I'm in front of you, virtually, I'm saying now for you, okay? So I was very lucky that to make a postdoc with Professor Maria Ruas at the same time that Bárbara. So we were able to see that actually this connection between the special points and critical points happens not only in the delta fiber, but also at the central fiber. So that's that result with at the zero fiber. All right. Let me see. Okay, I'm late. Yes. And then our corollary that we have is that since the Chern number is like here, right? So since the Chern number is the number of Morse critical points of emulsification of F1 over here, and remember, when we look at the critical set of F1 over this type of set, we have only the origin. So looking at F1 restricted to the regular part of X intercepted by the zeros of F2, we have only isolated singularity that might be degenerated. So we take the emulsification, we explode it only in the non-degenerated critical points, and these points are counting by the number of Morse critical points. Okay, this is already something, but it's also the Euler obstruction of the function F1. All right, so this is only a connection, right? Because the characterization was made by Saad, Tibarni, Verzobis. So this is only a corollary, but it's a beautiful equality between these two invariants. So very quickly, because I am super late. Oh, no, 30, but it's still I talk too much. The thing is that where is the lucky part of my postdoc, making my postdoc with Bárbara? The thing is that Bárbara also worked with an invariant associated to a function with non-isolated singularities, and it's perfect. So the invariant that she worked with a lot of other things, but I'm focusing in the relative Bruce-Roberts number, which is computed with this dimension over here. I'm not going to, I just need you to see that, to consider that we have an algebraic formula, an algebraic definition for the relative Bruce-Roberts number, okay? And we were able to connect, to give an algebraic formula for the Chern obstruction, like this one. This was the equality obtained. So it's the Chern number of the F1 on this intersection, given by this difference of relative Bruce-Roberts number. One computed over F1 and the other computed over a generic linear form L, for a form generic enough. When I say that we gave an algebraic formula, it is not kind of, okay, Eblin and Guzenzade also gave an algebraic formula for the Chern obstruction. This is an alternative. It is another algebraic characterization for the Chern obstruction in this setting. All right, and I'm saying this because it was quite nice for us to see that in the ICES case, when we have an isolated complete intersection singularity, we have proved by Eblin and Guzenzade, we have this formula, a difference of indexes. This is the GSV index, all right, which also have a algebraic characterization. This is why I'm saying that there is an algebraic formula already, but it's different invariants, all right? So they prove this difference between the Chern obstruction is this difference of indexes. And it's very nice because, see, the index over here is computed over the DF1 minus the index over the generic linear form L. And here we have the Bruce-Roberts number computed over F1 and minus the relative Bruce-Roberts number computed over L. So it's a nice I don't know, side by side. Okay, it's a nice side by side formula to see that things are in math are usually very connected, right? Just to finish, I'm just, since the title is saying end applications, this is the application I'm saying, which was the use of the Chern number to compute a number of cusps. So if we have a finitely determinate map germ, and we have a collection of one differential forms, df1, one of the sets is df1, df2, and the other one df1, the delta, where delta is the determinant of the Jacobian matrix of F. So the Chern number can be used to compute the number of cusps, or we can compute the Chern number by the number of cusps and the Müller number of the function f1. Since over here we are in C2, right? The Müller number is defined and everything. All right, so this is the quick application of this work, joined with Barbara and Cidinha. And this is it. Thank you.